Good morning, everybody. I really hope that first or second cup of coffee is really starting to kick in and you're excited about geospatial analytics. Oh, there we go. So my talk today is about geospatial analytics at scale for telecommunications. So first I'm going to go over some geospatial use cases for the telecom sector, then dive into some relevant open source data sets to tackle those use cases so that you can go home and start your own journey, and then talk about different methods for doing it at scale. So while this is not all-encompassing for all the different geospatial use cases for telecoms, I chose these four because they have a strong impact on customer satisfaction and business planning. So within the mobile sector, something that we really worry about are signal obstructions, and one of the most common is being inside of a building or being indoors. So perhaps you're driving your car, you have a great cellular connection, you pull into a parking garage, and then all of a sudden you start buffering, or the music starts not playing as well, and so that's something that is a negative experience. Similarly, when somebody's in transit, you can think of like in a train or the subway. In New York is actually quite good, but in MARTA, where I'm from, in Atlanta, you lose your connection quite often. It might go to SOS, or there's another thing that can happen, which is you have a cellular connection, you get to your stop, maybe there's a local Wi-Fi hotspot that you've connected to prior, but you're not getting off at that station this time, and so you leave again. And so you have a negative experience from going from your cellular connection to your Wi-Fi connection, and then quickly transitioning again. Similarly, you have signal coverage. So we all have our cell phone. To level set people's expectations, you know how good your cell phone coverage is based off of the number of bars on your cell phone. And that's really all geospatial analytics can calculate that, because it's all about proximity to a cell tower. If you're in line of sight of the cell tower, so there's no obstruction, and then if you're in the right angle for that transmitter. So here are some open source data sets that can really solve these different geospatial use cases, and I'll just briefly go over them. First, we have the US Census that we're probably all familiar with. It gives us good demographic data about our users. It can also be used as spatial partitioning, which I might get into later. Then we have Overture building data sets. So if you're indoors, US government transit, so these are going to be like bus routes, the subway, the metro. Then we have FCC Broadband. So it's a great data set for understanding the capabilities of the different telecoms providers in a certain area. Great for geospatial work. And then our team likes to call it crowdsourced analytics. So when somebody takes a speed test, that OOKLA captures that data, and then they can aggregate it. In this case, it's aggregated by quad bins to determine what is the average download or upload speed in a particular area. Then we have OpenCelliD. So this, again, crowdsourced, people are self-reporting where they see cell towers and the different types of transmitters for the different technology capabilities of those cell towers. So great to calculate that distance, that infrastructure. And I'm just going to go real back to this slide. Sorry. So one thing, I covered the three use cases for customer experience, but I didn't really get into the distance to infrastructure in terms of network expansion. So in network expansion, you really want to know where your customers are located and if you're able to service them. So one example might be for fiber and cable, am I 500 feet, is a home within 500 feet of a buffer polygon? And then they could be considered serviceable. If it's greater than 500 feet, then you're not serviceable. And so this is great for planning. If you're creating more fiber, then you know who your customers are going to potentially be, or if you have reporting needs like the FCC Broadband, is this person actually serviceable for grants or not? So just wanted to cover that one quickly. All right. So as analysts, we're always looking to solve problems or determine different KPIs. And to solve problems, you really got to look for that causation. So I like to call it the search for causation. So I'm just going to briefly go through this example. Right here, we have a map with the census to get that demographic information. We might want to add in roads to see if our customer was in transit. but maybe that still didn't solve a problem, so now we're adding in another layer. This is the Overture building data sets. Are these people indoors or not? And then, we add in the OpenCell information. Should they be getting good coverage in the area? Or the pink lines are showing transit in terms of the subway. So while this may not actually give us causation, it's going to give us really high correlation, and that can be good enough for our purposes, mitigating any customer experience problems. So that's the search for causation. But we really want to do this at scale. That example was all within a certain census block. But what if we want to do this across the entire country? So to do analytics at scale, first you have to determine what is your data warehousing or your data compute stack. So almost all the major cloud providers are successful here and are good options. You got AWS, GCP, Databricks, Snowflake. If your company is into it, you got on-prem services where you can have min.io for storage and then Kubernetes clusters for compute. I highly recommend choosing a platform that integrates nicely with Apache Spark. Our team has found it's greatly increased the efficiency of our queries, and it integrates well with Apache Sedona, which is an open source geospatial library. So once you've decided on your data warehousing, your data compute stack, then you got to be concerned about your data modeling. So if you're doing this at scale, you're using terabytes or petabytes of data, you really have to use spatial partitioning or spatial indexing for performant querying. I always like to think of spatial partitioning. You have this giant table, and you're making it into smaller chunks so that your cluster can process it in parallel. And then spatial indexing, it's kind of like a hash map. Instead of doing your join against the entire table, you find your index, and then you're just processing that segment of information. And fortunately, Apache Sedona supports both of these techniques, and it's very developer friendly. You're able to use Python, Spatial SQL, and Scala. And so to just go through a quick ETL toy example, if you have something like GeoParquet or a Parquet format that's native to Spark, you get right into your ETL doing spatial joins using Apache Sedona. Otherwise, you can use your ingest or connector tool of choice. I really love Python and GeoPandas because it can read in pretty much any different type of spatial data set. And then it's one line to go from your GeoPandas data frame to a PySpark data frame, which then Apache Sedona can go ahead and process. And you'll notice we have viz data optimization. So I always feel like my analytics aren't true or real until they've been copy-pasted to Excel and copy-pasted to a PowerPoint. Or you can go the dashboard route. And if you go the dashboard route, then there's a couple key steps to really make performant geospatial dashboards. So you see there's a split here between the statistics data and your geometry primary key. So let's think about speed tests for a moment. If you had 1,000 speed tests in a particular building, and that's in your table, you don't really want to render that building polygon 1,000 times. You really just want to render that building once and then get your aggregate statistics from the 1,000 speed tests. So I may start with one table that has all my information, but when I start going to the dashboard, I'm going to create maybe 5 or 10 different tables to make sure that all my geometries are only ever rendered once, and then they have a primary key that links them back to the statistics that are relevant. After that, then you have application-specific optimizations, so things like zoom level. If I'm at a viewport that's looking across the entirety of the United States, then I probably don't want to render every single Overture building. It just won't be very informative for the end user or myself. And so I'm going to do something like a heat map or H3 that shows hotspots. And then when you drill down, you can start rendering those building polygons. Similarly, when we're rendering your resolution of geometry when you're doing your joins, you may want 1 meter or sub 1 meter accuracy depending on your use case. But maybe for the visualization, you don't need that. And so you can reduce your precision for the end user, and that's going to also increase the performance of that dashboard. It's going to refresh really quickly. And then finally, I have filters here, but really I mean layers. Don't be afraid of having a lot of different layers within your geospatial dashboards. That's exactly how they're supposed to work, and that relates back to those unique geometries. All right, and this is My last slide, I really love it. It's a good architectural slide that comes from Apache Sedona. It goes through the different data warehousing, the different spatial formats that are compatible, the compute, so Apache Spark, the cluster capabilities, and then onto the developer tools, really friendly. And so I just ask when you go home, download Docker, pull the Apache Sedona Docker image, download some of those open source data sets, and start your own journey in spatial analytics. Thanks.